Yellowstone National Park is world famous for its beauty. Millions of visitors head there each year to catch a glimpse of its geysers, hot springs, bison, bears, and wolves. But if you ask any geologist, they'll tell you that what makes Yellowstone truly remarkable isn't the wildlife or even the pretty scenery, but rather what lies beneath the park's seemingly untamed wilderness, one of the largest and most powerful volcanoes on the planet. In fact, Yellowstone sits atop what's known as the Yellowstone Caldera, a massive crater formed by the cataclysmic eruption of a supervolcano some 640,000 years ago. The resulting debris covered much of the western United States in ash and pumice. And though it may be hard to believe, the effects of that ancient blast still reverberate across the globe today. It's just one example of how, over the past 2 million years, Yellowstone's eruptions have profoundly shaped our planet and our lives. In this episode, we're going to explore Yellowstone's volcanic legacy, how past eruptions continue to influence life on Earth today. But first, let me introduce myself. I'm the host, and this is Crash Course Geography, a production of Complexly in partnership with the National Park Service. Yellowstone National Park covers more than 2.2 million acres in the northwest corner of the United States, straddling the border between Wyoming and Montana and dipping into Idaho. The park encompasses everything from Yellowstone Lake, the country's largest high-elevation lake, to the Grand Canyon of the Yellowstone, which is deeper than the Grand Canyon in Arizona. But what the park is perhaps best known for are its geothermal features, like Old Faithful Geyser, which erupts every 90 minutes or so. And while Old Faithful is certainly a wonder to behold, it's really just a minor league player in the park's volcanic hierarchy. That's because Yellowstone rests atop a so-called supervolcano. In fact, it's the largest active volcano in the contiguous United States and ranks as the 21st largest volcano on Earth. The thing to know about supervolcanoes is that they can have a major impact on climate. Unlike regular old volcanoes, which typically build their cones layer upon layer with lava flows and produce relatively small eruptions, supervolcanoes tend to have violent, explosive eruptions that eject an incredible amount of ash and gases into the atmosphere. To qualify as a supervolcanic eruption, the explosion has to register a 7 or higher on the Volcanic Explosivity Index, or VE. For reference, Mount St. Helens, which erupted in 1980, ranks as a 5 on the index. Even the relatively minor eruption of Novarupta in Alaska in 1912, which ejected more than 3.6 cubic miles of material into the air, only registers as a 6. Supervolcanic eruptions, on the other hand, are so large that they're literally earth-shattering. They eject more than 240 cubic miles of material into the atmosphere and leave behind craters more than 60 miles across. Volcanic eruptions of this magnitude don't happen often. There have only been about 12 since the Pleistocene epoch began 2.6 million years ago, and fewer than 10 of those were powerful enough to cover the western United States in ash and pumice. But at least 3 of these super eruptions did occur within what we now call North America, including the one that created the Yellowstone caldera. This was no small event. The eruption ejected an estimated 2,800 cubic miles of material and left behind a crater more than 43 miles wide. That's so big that if you put 16 American football fields end to end, you still wouldn't be able to cross it. The sheer scale of this eruption meant that unlike smaller volcanoes whose slopes are relatively gentle, the sides of the Yellowstone caldera are incredibly steep. Over time, however, layers of ash and mud have filled the bottom of the caldera, creating a magma chamber that's now home to several smaller but still very active volcanoes. These include the aptly named Biscuit Volcano, which last erupted in 1400 CE, and the aptly named Black Sand Basin, which last erupted in 1300 CE. Of course, these names reflect not just the locations of these smaller volcanoes, but also the type of eruption that they produce. While the vast majority of Yellowstone's eruptions are relatively small and lava flows out of the top of the cone, these more explosive eruptions send ash and cinders billowing into the air. Because these materials are so lightweight, they quickly fall back to the ground around Yellowstone, blanketing the surrounding landscape in a dark layer of ash and fine grain called tuff. It's this process that gives many of Yellowstone's eruptions their distinctive black sand appearance. Now, if you've ever tried to sweep up a pile of sand, you know how annoying it can be when the grains slip through your broom and settle back down on the floor. Something similar happens after a supervolcanic eruption. Fine particles like dust and ash are so light that they stay suspended in the atmosphere for weeks, months, or even years. During that time, they reflect and absorb sunlight, which can cause temperatures around the world to drop by several degrees. This phenomenon is known as volcanic winter, and it's thought to be one of the major factors that led to the end of the Pleistocene epoch. Some 11,700 years ago, the Earth entered a warmer period known as the Holocene. Temperatures rose around the world, and the vast ice sheets that had covered much of North America and Northern Europe began to melt. While there's some debate as to whether or not Yellowstone played a role in this shift, most scientists agree that the supereruption some 640,000 years ago did play a significant part in setting the stage. That's because the ash and gases that shot into the sky during this eruption not only blanketed North America in darkness, but also triggered a cascade of environmental changes. First, the finer materials made their way into groundwater, where they reacted with minerals to form new compounds. These compounds then seeped into local waterways, creating what scientists call a pulse of Yellowstone water. By studying the chemical composition of streams and rivers around Yellowstone, scientists were able to identify this pulse of water and trace it downstream to the Pacific Ocean. But as the water flowed over rocks and soil, it picked up dissolved minerals, nitrogen, phosphorus, and carbon, all of which serve as nutrients for phytoplankton in the ocean. In fact, scientists estimate that the nutrient load from this one eruption was enough to fertilize phytoplankton growth for hundreds of miles along the coast of what's now the Pacific Northwest for decades. This pulse of nutrients then spread further south along the coast of California, where it helped trigger a major algal bloom. This bloom lasted for generations, fundamentally altering the species composition of marine life in the region. In fact, studies show that the ratio of calcium to magnesium in ocean sediments changed dramatically around the time of the Yellowstone eruption, reflecting a sudden abundance of phytoplankton. And these microscopic organisms aren't the only ones that benefited from the supereruption. Scientists also found a sharp increase in the remains of larger marine animals like diatoms, radiolaria, and foraminifera, suggesting that there was a subsequent surge in zooplankton and fish populations. So even though the Yellowstone eruption didn't directly cause the end of the Pleistocene epoch, it did leave a clear mark on life in the Pacific Ocean. And it's far from the only example of how past eruptions have influenced life on Earth. Today, for example, scientists think that increased volcanic activity in the Atlantic Ocean during the Younger Dryas period caused global temperatures to plummet and glaciers to advance once again. Similarly, the 1815 eruption of Mount Tambora in Indonesia, which is considered the largest volcanic eruption in recorded human history, caused temperatures to drop as much as 3 degrees Celsius below normal for 7 years. This even led to widespread crop failures and famine in places as far away as Europe and North Africa. To learn more about these events and others like them, you can check out our episode on volcanoes. And while it might be tempting to see these examples of climatic catastrophe as relics of the past, it's important to remember that similar events are still happening today. Smaller eruptions, like the 1980 eruption of Mount Steady Helens, can still have a major impact on nearby ecosystems, shaping the types of plants and animals that can live there. And even though there's no evidence that the Yellowstone supervolcano will erupt anytime soon, scientists do predict that when it does, the entire planet will feel it. Thanks for watching this episode of Crash Course Geography, which is filmed at the Team Sandoval Pier Studio and was made in partnership with the National Park Service as part of their 100th anniversary celebration. You want to help keep this series free for everyone forever? You can join our community on a crowdfunding platform.